Okay, as if that last video wasn't enough, now we have how to actually write a Taylor series without all of that insanity of the last lesson. So there's a structure here, there's a setup for you to write a Taylor series on your own. And also I threw a new word up there called a MacLaurin series. It's nothing to get confused about. It's actually just semantics, two different ways of saying basically the same thing. Now, I'm gonna show you now how to write a general series. This strategy works no matter what the series is, whether it's geometric or not geometric. Whatever function we have can be written with a MacLaurin or Taylor series. Taylor series is the broad version of the word. MacLaurin is a little bit more specific, but it's actually what we end up using kind of the most. I'll explain in just a second. What our big goal is to be able to write a series for e to the x. And I wrote centered at 0, which I'll explain in a second. So we already have a series now for sine. We have a series for cosine, which we built off of sine. Maybe we'll also try to write a series for cosine using this strategy, but first we'll start with e to the x. But we will not have to build this the way I built that series for sine. What I get to do instead is understand how a MacLaurin or Taylor series works. So I'm going to be putting my notes under MacLaurin series. These two are the same thing. The difference is a MacLaurin series is centered at 0, which is how everything has been centered that we've been doing. So even when we wrote the series for sine the other day or yesterday or whatever, what I had said was, here's sine x. If I took the series for sine, it matches the most strongly the closer I am to the origin. That's because we centered our series at 0. We just didn't really talk about there being any other options. But let's say we use the first 5 terms of the series for sine x, whatever they were. So we had a pretty good match for a while, and then we veered off, and then we veered off. We had a really strong match in here. Well, we had an exact match at 0, and that would be called centering at 0. I can, if I want to, and sometimes I'll be asked to, find a series centered somewhere else. So let's say I have a sine function, but I want to center my series at pi. If my series is centered at pi, then that means I'm going to have the strongest match at pi. And then eventually the series is going to go off, and that's going to go off. Oops, terrible picture. But eventually the blue is the series. It'll go off and the function will stay. And there'll be a close match here centered at pi. So that's the difference. This would be centered at some other number other than 0. So in this case, pi, or we're centered just at 0. So for right now, we're just going to talk about centering ourselves at 0. I'll probably put the other format in for centered at something other than 0. Ah, dang it. I didn't mean to get rid of that. Is there an undo in Cami? I'm sure there is. You're probably yelling at me, but I just don't know where it is. Minus, plus. How do you undo? Whew. Okay. I really didn't want that to go away. Watch me make it go away again. Nope. Okay. Good enough. Okay. So, oh my gosh. Oh, so funny. Okay. So MacLaurin series. To find a MacLaurin series, you are going to be finding the function, the value of the function at 0, and as many derivatives as are required of that function at 0 to find the number of terms that you need. What I mean by that is you're going to take the function that you're given, and you're going to evaluate that function at x equals 0, and you're going to get a value. You're going to take the derivative of that function, and you're going to evaluate that at 0, and that's what we're going to call f prime of 0. Then we're going to find the second derivative of the function, evaluate that at 0, and that's going to give us f double prime of 0. We're going to keep going however far we need to go, and we're going to use these values to find our series. The setup of the series looks like this. To find a series using the MacLaurin technique, the first term of the series is going to just be f of 0. The second term of the series is going to be the first derivative at 0 times x to the first over 1 factorial. Technically, I'll go back to that. The next term is going to be the second derivative of f at 0 times x squared over 2 factorial. The next term is going to be the third derivative of f at 0 times x to the third over 3 factorial. And so on, and so on. Oops, that's a ... and so on. That's it. This first term might look weird. It might look like the rest of the terms are different, but it's not. This first term, let me just give myself more room, is really just f of 0 times x to the 0 over 0 factorial. It's just that 0 factorial is equal to 1, and x to the 0 is just 1. So we don't have to have them in there, but that does follow the same pattern. It's not like the first term's different from everything else. It's just that these guys all cancel out, so we don't put them. So to make that make any sense, let's go skip to writing the series for e to the x using this MacLaurin series. So to write a series for e to the x, the first thing, let's say I want the first 4 terms of the series. The first thing I need to do is find f of 0 and the first 4 derivatives. So I'm going to start by saying, okay, f of x is e to the x. Let's evaluate that at x equals 0, and I get 1. The first derivative of f is still e to the x. The derivative of e to the x is e to the x. That evaluated at 0 is still 1. Whoops. The second derivative of x is e to the x. Evaluated at x equals 0 is still 1. So it turns out all of these derivatives are going to be the same. So all of my f of 0s, f prime of 0s are going to be 1. So when I write my series for e to the x, I'm going to follow this setup. The first term of the series is going to be f of 0. So my series is going to be 1 plus the second term is the first derivative of f at 0 times x to the first over 1 factorial. My first derivative of f is 1, so I'm going to have 1 x to the first over 1 factorial. Then I have the second derivative of f at 0 times x to the second over 2 factorial, and so on. This is the series for e to the x. Let's clean it up a little bit. So e to the x equals 1 plus x squared over 2 factorial plus x to the third over 3 factorial, and so on, the general term being x to the n over n factorial. That's e to the x. Boom. You now have a series for e to the x. So now we can add that to the other series that we know. E to the x, sine x, cosine x, now we know them all. I could have used a Taylor series or MacLaurin series to write the series for sine of x. Let's do that right now just to see and confirm that it actually works. We know what the series for sine x is supposed to be, or we kind of know, we probably forget at this point. But let's see if we can figure it out. So let's say we're going to write the series for sine x, and we don't know what it is right now. So f of x is the sine of x. Evaluated at 0 is going to be 0. The first derivative of f is cosine. Evaluated at 0 is 1. The second derivative of f is negative sine. Evaluated at 0 is 0. The third derivative of f is negative cosine. Evaluated at 0 is negative 1. The fourth derivative of f is sine. Evaluated at 0 is 0. And the fifth derivative of f is cosine of x. Evaluated at 0 is 1. All right, let's go write the series. So we're going to start with f of 0 plus the first derivative of 0 times x to the first over 1 factorial plus the second derivative of 0 times x squared over 2 factorial plus the third derivative, x to the third over 3 factorial plus the fourth derivative plus the fifth derivative. So on and so on. So like we were saying in class, when at any term that fell out to be 0, we don't include that. We're not going to include any of these in our final series. We're going to only include the non-zero terms. So sine of x is x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, and so on. Yeah, that's what we got for sine. And we could write that general term even if we didn't have our notes. We need that alternator, or I forget what Paul called it, the switcher. We need an x to the 2n plus 1 over 2n plus 1 factorial. We need to start this at 0 so that my numbers work. And then I'm going to start this at n. First term's positive, we're set. So this is the shortcut to the long version from yesterday's video. This is the shortcut to writing the Taylor series for sine, or MacLaurin series. So I keep using those words interchangeably. MacLaurin series just means I centered it at 0. A Taylor series is also centered at some other number, but I could say this is a Taylor series centered at 0, and that's fine. But I could also just say MacLaurin, and then I don't have to say where it's centered. If I say MacLaurin, we assume we centered it at 0. If I say Taylor, we have to be told where to center it at. Okay. We're not going to do Taylor today. We're going to save Taylor for tomorrow. And what I want you to try now is I want you to practice, can you write the series for cosine x using Taylor series or MacLaurin centered at 0? Can you go through this process, and do you end up getting the same thing you got when we did it by taking the derivative of sine? So that's it for today. Can you do that? And we'll pick back up tomorrow.